Hello, welcome back guys. Today we're going to be doing a differential rate law problem plus integrated law problem. I'm going to distinguish between them as two separate questions in this problem. So differential, so I just put a side note here as you can see on your right of the table, and the note says that the differential rate law depends on the concentration of the reactants, or how the rate depends on the concentration of the reactants. So how the rate of the products will change as the concentration of the reactant change over time, as being the reaction concentration or the reactant concentration as the independent factor, and the independent variable, and the dependent variable will be the reaction rate. On the other hand, the integrated rate law will tell you how the concentration of the reactants depends on time, as time being the independent variable and the concentration of the reactants as the dependent variable. So how the reaction or how the concentration of the reactants will be consumed over time to make the products. So let's start here. So we are having reactions in which you have CH3COCH, which is an acetate reacts with bromine, Br2, and you have a catalyst, which is the hydronium, and it's going to give you a product. Then this product will be CH3COCH2Br plus water plus bromide. So let's write the reaction to give a sense of what we just said. So you have, one second, I'm taking difficulties right now here. Okay, here we go. So we have CH3 COCH minus 1 plus Br2 plus hydronia, and this the whole thing goes to CH3CO CH2Br plus H2O plus Br. So that's the reaction. Br in this case could be radical, or like having like 8 electrons, so it doesn't have a charge, or to just aqueous. So just put aqueous so we don't confuse anybody here. And these are the reaction. So we just focus on the main question. So we need to find the differential rate law. So when you turn on differential rate law, just like here, we need to find or hold, since we have 3 reactants, we need to hold 2 of them constant, or see where they don't change, and use the one that does change. Like, let's do an example without like keep explaining the problem. So the differential rate law, which is maybe in this case will be just R, will equals, we have the concentration of CH3 COCH minus 1 initial times Br2 initial times hydronium. So I'm just going to put H plus instead of putting H3O plus initial, and we're going to divide all this. Remember that you have a K, which is rate constant, and it's going to be equal for both concentration, initial and final. And in this case we have CH3 COCH minus 1 final, Br final, or Br2 final, we'll forget the 2 in both cases, and we have the H plus also final. So in this case so let's start with the CH3COCH minus 1. So we're going to see what it changes. It changes between trial 1 and trial 4, trial 2 and trial 4, trial 3 and trial 4. But which one we gonna pick? So we need, as I said, we need to hold the other one constant. So if you look at the last two trials, the other two are constant, like 0.05 molarity moles, 0.05 moles, or molarity, sorry, and 0.2 molarity, and 0.2 molarity here, which is a concentration. So let's use the trial number, so we just highlight it here. So let's use this trial number 3 and trial number 4. So this is going to be equal to, okay, so first of all, as we said that K is constant for both the rate of reaction, is constant for both of them, so you can just like cross out the K's. And we end up with getting the, and since we know that Br2 is held constant and KH plus, which is hydronium, is held constant, we can cross them out. And remember, since you're doing rate initial, it's going to be also divided by rate final. So CH3COCH minus initial is 0.3 divided by final is 0.4 times. I'm just going to put the BR2, which is 0.005 divided by 0.005, and this one gets cancelled out into 1. And you have the 0.2 hydronium, oh my god, here is all the way down, over divided by 0.2, which and they will cancel as well. And this is going to be whole thing equal to the rate, which is initial, which is right here. This is the rate here, this one, and this one as well, which is 0.00012 divided by 0.0000212. So 0.3 divided by 0.4, using the calculator, 0.3 divided by 0.4 is 0.75. So we got 0.75, which is pretty much 3 over 4, is 0.75. Another one is 0.00012 divided by 0.000030212 is going to be equal to 0.566. And now we're going to solve this problem. So how are we going to solve this problem? So how does this will equal that? So in this case, we need to use some techniques, which mathematical techniques in other words. Mathematical techniques will be, so we just drop the axis here, which is like the power. And 0.75 is raised to a certain power to give you 0.566. So in this case, you take natural log for both sides. So you end up with getting, if you take natural log of the 0.566, you end up getting minus 0.0 or minus 569 with 0 here and 0.2. And the other, so when you take natural log, so our equation is taking natural log of both sides for the equation. Take natural log of 0.75, use, so the x, whatever is power, you can pull out of the natural log and make it a constant. Or not a constant, like a coefficient. And you will end up with the natural log of 0.75. So natural log 0.75 is 0.288. Now we do the division, and it's negative as well here. So how you solve now? You divide by 288 both sides to get x. So in this case, x will be equal to 0.569 divided, or minus 0.569 divided by 0.288, or minus 2.8, and here we're getting almost 2. But remember, we're in the business of using integers, the rate law, it's 1.975, which is close enough to 2. So now we have the first x. So remember, these also have power, so this is going to be y, it's going to be z, it's going to be z. Okay? So, and you calculate them out, the y and the z's, because both concentrations for hydronium and bromine are equal. So we just write on the side the CH3COCH minus, it has the x1 and it's going to end up with being 2. So just put now on the top here, right here, and just find the marker x. Okay, that's a bad color here. So let's use green or something just to make it be able to see it. There we go. So we have x here, y here, z here. So now let's do some housekeeping and clean some of the stuff that we wrote. So we're gonna erase all this. Here we go. Let me fix this as well real quick. And we end up. Now we're gonna solve for PR, which is y. So hope you can see that mentally, that BR will be the first and the second trial. Why? Because it is different and they want a constant at this trial. So we got rate initial divided by rate final equals so instead of writing, I'll just write it, the CH3COCH minus 1 the power of y divided, and don't forget the rate constant, divided by 2, that's the initial, divided by the final, which is CH3COCH minus 1, or final, and extended division sign, oops, extended division sign, and that should be x here, and that should be x here as well, divided by BR 2 to the power of y, BR 2 to the power of y, initial and final, and hydronium, and we use the letter Z to space its power, and we have initial and final. So I don't need to go again and tell you why I cancel out the case, because rate constant is called rate constant, the rate constant, so it's constant for both reactions or both trials. And you know that we choose this one will get cancelled out, and this will get cancelled out, because you can see from the first and second trial that 0.3 will get cancelled out together, and 0.05 for the hydrogen will cancel out together. So you end up getting this. So what are you getting? So you're gonna have BR2 to the y, so this is gonna be the same thing as BR2 divided by BR2 initial final, sorry, and initial here. That's the power of y equals R initial over R final. So BR2 initial in this case will be 0.05, and final is 0.0 or 0.1, raised to the power of y, and the rate of the reaction is 0.000000595 divided by 0.0000595, and this one is going to be equal to 1. So whenever you see something equals to 1 and you end up in the right left side with something that is raised to the power, you will automatically know that y is going to be 0, because how you get 1 when you have exponential function is always by raising or making the exponent equals to 1, or the power equals to 0. So the whole thing here equals to raise to the power of 0 will give you 1. So you don't really need to do any math here, just like since you get 1 on the right side, you automatically know that the power or the exponent on the left side is equals to 0. So we solve for y, and y equals to 0. So now let's do some deep cleaning now. And here is the PR plus BR. So now we end up with solving for z now. This is the last one. So when is z is different and the other one are equal? So you need to think about this one. So you got 0.05 and 0.2. So if you look at the first two terms, they're equal, the last two terms are equal. So you need to use the, which ones? The second one, which is 0.05 divided by 0.2. Oh, you can use the first. Okay, so in this case we're using the first one and the third one, because 0.05 divided by 0.2 and have the other one constants. So you just use the first and the third. So again, back to writing. I'm not writing the correct equation again, so just using the first and the third. So 0.0000595 divided by 0.000 3 zeros, 1, 2, and then equal to, okay, so we have 0.05 to the power of z divided by, or the 0.05 divided by 0.2, everything is power of z. So let's see what you get here now. So the 0.0000595 divided by 0.00012, you end up getting almost a half, which is 4.495, the 0.496, and that should be equal to 0.05 divided by 0.2 is equals to 0.25, and this should be raised to the power of z. How you solve it? Natural log. So you take natural log, you pull the z out, turn over using z here, 0.25, and equals to natural log of 0.496. Okay. So you have two ways to solve this. Either you take natural log of each side, or you do the division, which you end up with getting natural log 0.496 minus 0.25 equals z. So let's do the subtraction one. So whenever you divide natural log by natural log, you take the difference between or you just do numerator minus denominator arguments. So 0.496 minus 0.25, natural log of this answer. The answer is everything minus 1.4. So let me double check if we did the math right. So natural log of 0.496 divided by natural log 0.25, which is a half. So So it should be a half, so something funky happened right here in the division. So if we did them separately, so z will be equals to 0.5. So let's just put z here, equals 0.5. So the power will be like half, which is square, half is equal, power of half is equal to square root. And let's do it again. So natural log of 0.496 minus 0.25. Okay, natural log of 0.25 minus 0.496. So there's a problem here that I made a small mistake, which is you cannot do this. This property is done wrong because you need to have both arguments inside the natural log. So you need to have. So let me explain that to you. So ln x over y is something as ln x minus ln of y. So that's the property. So, but in our case, it's not this. It is ln x divided by ln y. So there's two separate functions here. So we can't do that. And so we got just focus back in the chemistry. So just erase all that now, and just forget the z. So now let's write the rate law. So differential rate law, or general rate law. So R equals last two things, which is K CH3 COCH minus 1 power of the, how much is y is 2. The other one we don't need to write it because BR2 to the power of 0 is just 1, so it won't make a difference. But you need, if you want to write it like that, 0 and it goes out to 1, that's fine. And the last one will be H3O plus the power of 0.5. Here we go. Now we need to evaluate K. So to evaluate K, just substitute any of these lines. So I'm going to just substitute the third line because, like, it has 3012, 0.0012. I don't know, like, we'll deal with like 5 small places. So R equals to the third line, 0.00012 equals K is unknown. CH3COCH minus 1 is 0.3, and it's going to be squared, of course. And the hydronium, which is H plus or H3O plus, is 0.2, the power of, and just take the square root of it. Because X, the 0.5 is the same thing as root X. So let's erase this handy dandy note. So let's do the math now. So you have 0.3 squared is 0.09 times the square root of 0.2 will give you 0.04. So back to the thing. Which is 0.04. I'll put 0.02 equal K equals 0.00012. So how you solve? Now just divide 0.00012 by the 0.0402, and you're getting this nice number. It's not nice. K equals 2.98 times 10 to the minus 3. So what's the unit of K? So unit of K in this case will be interesting because we know that the rate law or the rate is molarity by second equals the CH3CO CH minus 1 is going to be molarity squared times molarity to the power of 0.5. Okay, so you end up, and you have K here, and you end up dividing, so you get M and you know, like, we have the same base with some exponent 2.5 equals molarity over second, and you end up dividing this, you end up getting M divided by M to 2.5 times S. And remember, you just do subtraction and remember, let's go here. Remember, you have X divided by X 2.5 is same thing as X to the 1, which is here is 1 in this case, minus 2.5. Just erase this. Okay. And so now we end up with getting 1 over, you know, M to the 3 over 2 times S, which is seconds. So that's the unit of K. It's going to be 1 over M 3 over 2 or 2 or the 1.5, because 1 minus 2.5 is minus 1.5. Since the exponent is negative, it goes down the denominator times second. So that's the unit of S. Oh, sorry, K. So your K is this. So now what you do is just replace this K with this value. And if you do the math, you end up getting, if you do the multiplication of unit of K times the concentration squared times the concentration power of 0.5, you end up getting molarity per second. So that's it for the differential rate of law. I'll see you in the next video to do the integrated rate law. Thank you.